In this section, we are going to generalize our domain of integration. So let's say we have a function, f of x and y, that we want to integrate over some region D. And we can picture this as some sort of blob that's sitting in our plane. So this is our D. We do need D to be a bounded region. We need it, which means it doesn't go off to infinity, if you remember our definition from last chapter. And what that's going to mean for us here is that our region D is going to be contained in some rectangle. We can say we can put a rectangle, which we'll use R again, around this region D. So D is bounded and contained in rectangle R. Now, as an example, I'm going to go ahead and pick the function f of x, y is just equal to 2 minus x squared. And I'm going to look at a region D defined to be all the, I should just put this as equals, the set of all points x and y, where x squared plus y squared is less than or equal to 1. You can say that's our unit disk. If we're going to draw this, so if we draw the region, we can go ahead and just put the boundary, the unit circle that we have there. We want to look at points that are inside this region. And we want to look at the actual surface, f of x, y equals 2 minus x squared. That's this, well, it's a parabolic cylinder, technically. And we kind of want to get an idea of what exactly is happening only over the unit circle. Now I can go ahead and actually take this and use an if statement. That's kind of an interesting thing here. So I'm going to use the condition that x squared plus y squared is going to be less than 1. And then I'm going to tell it to give me all the values of fxy in that satisfy that condition. And it kind of can't really see it. You can see it right there a little bit. If I take that away, you can see it a little bit better. So it's showing me only the portion of that surface that's inside that circle. You can actually see the circle, or the disk, if I look at it from above. And what we're basically saying is, if we only consider the points that are below this little section, what is the volume of that region? Now, like I said, we're going to do this by looking at a rectangle around this. In this case, let's go ahead and take the square. I'm going to take a square that's a little bit bigger than what we have here. We could actually take smaller ones. But I'm going to go ahead and put in the points negative 2, 2, negative 2, negative 2, 2, 2, 2, and 2, negative 2. And then I can actually make the... I'm just going to go ahead and connect them with segments. I don't want it to shade in the square. Keep making segments. There we go. And let's take out all those labels. Okay. So I've made a square around my disk, and if I had a function that was defined on this square, I would know how to integrate it. I would know how to find the double integral of that function of two variables. And so that's what I'm going to do. I'm essentially going to take the function that I started with, this 2 minus x squared, and I'm going to turn it into a function over the rectangle instead. And I'm going to do that by defining a brand new function, which I'm going to call capital F x y. And this is going to be defined so that it will equal the function little f of xy when xy is in the disk. When it's, or well, not, I shouldn't say the disk. I guess in our example, it's going to be the disk. In general, it's just going to be this whatever blob that we have. So if we take a point in the rectangle somewhere and it happens to lie in the disk, then the value of the function will be whatever the value of little f was. If we take a point and it's not in the blob, but it's somewhere else in the rectangle, say somewhere out here, then the value that we'll assign to this capital F will just simply be 0. So this is in the disk, but or it's in the rectangle, but it's not in the disk. So this is now a function of two variables defined in a rectangle. We know how to take the double integral of that. Now it may not be a continuous function, and so we might actually have a few issues with continuity and stuff like that. But that's why when we introduced Fubini's theorem, we actually had the extra condition that not only is our function not only does it work for continuous functions, but it also works for functions that are continuous, except for maybe on a smooth curve or finitely many smooth curves. So if we were to actually take what we have and kind of just put in the points that are not. Let me go ahead and write this in. I'll come back in a second. Okay, so I've defined a new function that I've just put in here. This is saying that if we take points where x is between -2 and 2, y is between -2 and 2, and x squared plus y squared is greater than 1, so things that are not in the disk that we had before, then I'm just going to give it the value of 0. It did cut off the corners for some reason, but you can imagine what we have drawn here is this is capital F of x and y, where it's 0 if it's not inside the disk, but it's our function outside the disk. And so we've got this function that is continuous everywhere except for on the actual circle. It is definitely discontinuous there. We definitely have big jumps there. But it is a function in two variables, and we can integrate that thing. So we will essentially define little f to be integrable over the domain D if capital F is integrable over the rectangle R. And we'll say the double integral is just whatever the double integral of capital F is over the rectangle. So we're essentially leaning on our definition for rectangles to generalize to more general domains. Now, of course, this doesn't really tell us how to compute the double integral. In order to do that, we're going to actually talk about different possible types of regions, or at least different possible ways of defining the boundary of the region. And so we're going to split this up into two types. We're going to have a type 1 and a type 2. They use Roman numerals for this, so it'll look like type I and type II. But I'm just going to say type 1 and 2. Actually, let's do this on another page. So let's start with type 1. A region is of type 1 if it is the space between two functions of x. So let's say we have our axes. We're just looking at the region D itself right now. We're not working with the three-dimensional stuff. But we're saying that we have some function y equals. Actually, I'm going to put g1 on the bottom, so I'm going to call this one g2. We'll have a g1 down here. And our D is some region between these two functions. If the functions actually intersect, maybe that will actually be a place where we end. But in the most general case, we actually end up going between two fixed values of x. So this would be from x equals a to x equals b, and then the y values vary between these two functions. So this would be our region D. Or at least this is a an example of a type 1 region. We might write the region D in the form of xy, or points xy where x is between a and b. Maybe I should write. Maybe I should put this as a colon, not a comma. So points xy where x is between a and b, and y is between g1 of x and g2 of x. So anything that can be written in this form where g1 and g2 are functions, that's what we call a type 1 region. Let's go ahead and actually look at a particular example. I'm going to take as my g1 x squared minus 3x minus 1, and I'm going to take my g2 to be the square root of x, and we're going to look at x's between 1 and 3. So let's go ahead and actually graph these curves. So we had g1 of x was equal to x squared minus 3x minus 1. g2 of x was just the square root of x. We have two curves in there. They do have one intersection point. They don't intersect over here. Maybe if we actually treated this as x equals y squared instead of y equals x square root of x, we'd have another intersection point over here. But we don't really need that right here. We're going from x equals 1 to x equals 3. Those are essentially two lines, two vertical lines that we have in here. And we're looking at the region that's contained between all of that. So this region in here. In fact, I'm going to go ahead and use the integral function, or integral between. That'll allow me to shade it in. So it's the integral between these two functions of x between values 1 and 3. And I don't really need the value of that function. I just wanted to shade it in. But this is the region D that we're working with. It is a type 1 region. It's kind of a typical type 1 region. And we want to be able to work with this thing. Now, how are we going to actually turn this into a rectangle? Well, for one thing, we already have limits on our x's that we want to keep. We might as well just use 1 to 3 instead of going any bigger for our x's. For our y's, maybe we'll have to think a little bit more about it. Let's just pick some numbers that are definitely below our region and above our region. So I'm going to go from -4, because -3 is definitely not far enough down, and I'm going to go up to 2. And let's actually even just go ahead and plot points and just show that rectangle. So here I've plotted the points 1, 2, 3, 2, 1, -4, and 3, -4, and I connected them with segments. So you can kind of see the rectangle here containing our region without too much extra space. We could get a little bit smaller by shrinking our top and bottom, but it really won't make any difference overall. In fact, maybe I want to go ahead and clean this up and kind of remove stuff that's not even really needed. Some of the stuff on the sides that don't really form the boundary parts of our region. And there we go. We don't have any extra fluff anymore. So we're just looking at our region D that's contained in a rectangle, and we want to be able to integrate a function over that. Now, I haven't actually given you a function yet. I've only defined the region. So I'm going to go ahead and pick the function f of xy is equal to 3 plus 2x minus x squared plus y. And we're going to integrate that over this region, or at least figure out how we would integrate that over this region. May not go through all the actual steps of doing that. So here's the picture that we had before, but now it's in our 3D axes. We can go ahead and look at our function, our f of xy, which was 3 plus 2x minus x squared plus y. And why did you do that? Okay, there we go. I don't know why it didn't display the actual surface. It just kind of showed the grid lines on it. So we want to look at this particular surface, but we only want to look at the part that's in our region. If we can figure out exactly how to work with that, then we might be able to do something. Let's actually maybe only show that portion of it. Again, I had to use a complicated if statement to actually make that work, to get it to limit to that part. And unfortunately, it did kind of cut off the part down here at the tip, but hopefully you can at least get an idea of what's going on here. And I just noticed that what I had there, it did dip below the XY plane. Whatever reason, I must have changed something since I wrote down this example. So I've updated that to be 4 plus 2x minus x squared plus y. That'll allow it to just barely hit the XY plane. I want to be able to talk about volumes here. Not that this won't work in general, but I just as a first example, I want to be able to do that. So we've got this thing here, and we want to find the volume that's underneath this surface. Now, of course, that means that we define a function that is 0 on the parts that's not being covered. So 0 up here, 0 down here, and still follows the surface here even though it's not shown. What we're going to do is look at cross sections, just like we did when we derived our formulas in the last section, just in this new context. And this is going to work specifically since we made our region type 1, because that will let us look at cross sections where we keep x equal to some constant. So I defined a constant here that I can vary to look at different examples, but I'm going to look at x equals c. And I wanted that to be the plane x equals c. There we go. The plane x equals c. It's a plane that's cutting through our surface, and I can vary it as we go. It's going to have some intersection, which we can actually go ahead and look at what intersection we're making there. Let us actually make that a little bit more visible. So we have it's cutting off part of our surface, and then down here it's actually going to be 0 on both sides. Our function, capital F, staying 0 here, then jumping up here, following that line down. It's a line in this particular case, won't be in general, but then becoming 0 again down here. Stop flashing like that. Okay, so it's going to be 0, then this line, then it's going to be 0 again. That is a curve. Well, it's a graph of a function in a two-dimensional sense, and so we can actually integrate over it. So we have our little f here. We defined our capital F, where it's little f on D, and it's 0 on R except D. And we fixed some value of x, and we're going to integrate capital F with respect to y on that fixed x. Now, of course, capital F of xy is going between some c and d that we have. So we made our rectangle. X is going from A to B, and then y on our rectangle is going from C to D. So those are the values I'm going to use here, from C to D. So this is R. Let me put the D inside so it's a little bit clearer. Okay, so this is exactly what we did before, except we want to somehow go back to little f instead of capital F. But what we're going to realize here is because we're not, as we go from C to D, we're going through a part that's 0, and then we end up with part that's 0 over here. Really, the integral is only going to depend on the part that actually is inside of D. The part that's outside on either side is, we're just integrating 0, so it doesn't really matter. That part won't contribute to the integral. So really we're integrating capital F of xy on this smaller piece. Well, we need to figure out what those limits are. But if we are dealing with a particular value of x, the value of this point here, the y value that we're dealing with, is just g1 of x. The value of this point here, the y value there, is just g2 of x. So for a particular value of x, we're only integrating capital F from g1 of x to g2 of x. Now we're putting a variable in our limits here, but keep in mind we are just treating x as a constant, so it's not going to be a big problem. In fact, it's going to turn out to be exactly what will be the key to making things work overall. Now we're only integrating over the part that's actually in D, and when we're in D, capital F is just little f. So we'll go ahead and replace capital F with little f. And so we can say that the integral over that cross-section, that cross-sectional area, you could say, is this integral here, where we end up with variables in our limits. Of course, to find the double integral, remember we would integrate this. So say the double integral of f, capital F, over this rectangle, we saw was the integral of these integrals. Actually, let's just go ahead and put from C to D of capital F xy. It was dy, but then we're integrating this with respect to x, and that's going to be from a to b because those are the limits on our x's. So we're integrating this integral with respect to x, and then from a to b, and that was our double integral. This is the formula we got from Fubini's theorem. But this over here, we defined way back here, the integral of little f over d to be the integral big F over the rectangle. So this over here is just the double integral of little f of x, little f of xy over d. And then this over here, we'll go ahead and leave the integral of x from a to b alone and replace this integral in here with this formula that we derived in terms of little f. So this is going to be the integral from g1 of x to g2 of x of little f of xy with respect to y, and then with respect to x. So this is going to be our formula for actually computing integrals, or double integrals, over these type 1 regions. And if you want to look at how the book actually writes that out, it actually gives the formula for the notation for the type 1 region D, and then it writes down essentially what I've just written out here. But the point is that we turn this integral of f, little f, into an iterated integral that we can actually go ahead and do all the work with. Now, it will make it a little bit more complicated because we will be dealing with functions of x that will be... So, when we do this, we'll be integrating some formula with respect to y, like we did before, but then what we plug in for y won't be just numbers, but we'll be plugging in functions of x. That means we'll be introducing new functions into the result of the integration before we then go ahead and integrate again with respect to x. So that will that'll be more work for us, but it actually won't be anything new in terms of concepts. So we'll see how that goes when we get to some examples. Before we get to those examples, though, I do want to talk about the other type of region that we're going to be using, the so-called type 2. And really isn't a new type of region. What we're really doing here is interchanging the roles of x and y. We're essentially saying our region is defined not by two functions y in terms of x, but two functions x in terms of y. So this is x equals, say, h2 of y, and x equals h1 of y. And then our y values are going between two values, c and d. This would be our region D now. So you can say D here is a set of points x and y, where y is between c and d, and x is between h1 of y and h2 of y. Just kind of flip the order that we're doing x and y in. And this doesn't really change the process. It just means that we're going to make our rectangles in this direction this time. So I end up with an A and B like this. For x's, it's containing that rectangle. This time, instead of looking at cross sections where we keep x constant, we'd be looking at cross sections where we keep y constant. And so we'll end up with we'll end up with dx dy instead of dy dx, but we get a very similar formula. So the double integral over d is just going to be the integral from c to d with respect to y of the integral from h1 of y to h2 of y with respect to x. And equation 4 that they have listed here is essentially just what I wrote up here. It's this definition for d. So I'm not going to go through that process. It's exactly the same as what it was before. The book kind of skips through it as well, just because we're not really doing anything new. It's just whether or not we're looking at x or y as kind of our main thing, our main way of doing cross sections. And the reason why we give these names is because there are some regions that can be written as either a type 1 or type 2, and it actually will help us in some contexts to be able to look at either one and see which one would be the easiest one to work out, because integration can be a little bit messy in some cases. So like I'm saying, in some cases we'll be asking ourselves, well, can be type 1 or type 2, which one would be better? But then there's also some cases that cannot be written as either one. So let's actually draw a picture of something like that. So a case that's not either one of them. Might be something like, let's do something like this. If we had a region like this, if this was our D, we could put it into a rectangle, and so our definition still makes sense. But if we were to look at cross sections of this, we can't really think of this as either a type 1, because if it was a type 1, then all of our cross sections would, in the keeping x constant, would need to have only two intersections. So if we looked at vertical lines, well, some of these work very nicely, but if we look at a vertical line over here, we're hitting it at 4 different places. And that's going to be a problem. We're not, at that point, at that x value, we're not working with two functions. The region D is not the region between two different functions. It's between, you could say, 4 different functions in some sense. And that's a problem. If we wanted to think of this as type 2, we'd have to look at horizontal lines. And we have the exact same problem for a horizontal line like this. So this would not be a type 1 or a type 2. What we'd have to do on something like this is maybe split D up into multiple pieces. So if I want to leave the lines in there just for the PDF at the end. But if I were to essentially draw a similar one, actually let's make this a little bit more angular, be a little nicer to draw, something like that. If I wanted to work with this thing and I wanted to find an integral over this, what I could do is I could split this up into two pieces. And I kind of drew these to make sure that we could just make that straight line there. Essentially, the shape that I drew there can be made up of these two different triangles. And these two triangles are actually, well, this one is a type 1 or a type 2. We could actually use that for either one. This one down here is actually a little bit of an issue. We still don't have it as type 1 or type 2. Maybe we'd actually split this up into two more rectangles, or not rectangles, triangles. We have a triangle here and a triangle here. Both those are actually type 1 regions. So that's something that we might have to do if we have too complicated of a domain. And, well, we just work with that the way you'd think we would. When we have a region D, I'm just going to go ahead and put it in some D that we have here. Actually, let me put that up here. So this is our D, but D is made up of two pieces, say a D1 and a D2, where D1 and D2 don't overlap, except for maybe part of their boundary. I don't know. I mean, D1 might contain all of this boundary or none of it or just part of it. The boundary doesn't really matter. As long as their insides don't overlap, then the double integral of our function over the entire thing is just the sum of the integral over one piece plus the double integral over the other piece. And that shouldn't be too hard to think of. So if we're thinking about, say, the volume under this piece and the volume under this piece, well, the total volume would just be adding those together. And that does work even if we're not dealing with volumes. If we're dealing with something that goes negative, it still works just fine. I'm not really going to get into explaining that. The book doesn't prove it or anything like that either. But it is something to keep in mind if we don't have a very nice type 1 or type 2 region. That's what we might have to deal with. The book does go through some other properties, things like being able to take out constants or break over sums. Those should be fairly obvious, but you might want to look through those and see what those are all about. But I'm going to go ahead and leave this theory video here, and we'll get into some examples in the next video. And since I want to go through quite a few examples, I might have to split that up into multiple videos too. But this is just all the theory behind all this stuff. Now we want to actually set it into actual works, be able to work with this stuff. So I'll see you guys in the next video.